sometimes which is coming is your profile picture.
Oh, okay.
Not you. I don't know if it is your network or it is our network.
Me, I'm using the very good internet of the department. So most likely it's your network. Okay, so for starters, welcome. So the first part of the course, the Python bit. The Python part of the thing which is there, the material which is there on Python, that is not really computational physics. In this case, the Python is the tool we are going to use to communicate with the computer so that we can actually do the mathematics which we want to do. The whole thing here is computing. So we need to do these things using a computer, the way a computer would do whatever it is we want to do. So we need to have a way of talking to the computer, and that's where Python comes in, because Python is quite easy to use and it's also quite easy to understand, and basically that's why I chose it. And over many years, things which were very, very difficult in Python, some of those things have been made automatic. Not quite automatic, but close to automatic as far as we can get. So it's very, very convenient for you, especially some of the methods we're going to look at. You can actually just run a simple Python program, then the whole thing, maybe 1 or 2 lines, then your stuff actually happens. So it's very, very convenient for us so that we can see. Mr. Limpo, I think you need to get dressed or something. I don't know what's happening there. Yeah, so that we can actually see what's going on. Yeah. So there is material on Moodle. Okay. You have had material on Moodle starting from chapter 1 all the way up to, I think this is this is 15, up to chapter 13 or something. But some of it is not very finished. It's not finished quite a lot. It's not finished enough. But what's there, I think, is sufficient for us to actually get to do something useful. Okay? And today is when we start doing some of those useful things. And I'm going to share one of the notebooks which we're going to use. Yes. Yes.
It's online class for campus.
It's online. You want to sit? You can sit.
Okay.
Yeah. Okay, so where are we? So I'm going to share my screen. Okay. So there we have solutions to nonlinear equations. Okay. Linear equations are basically straight lines. Linear equations of the form y or f of x is equals to ax plus b, where a is the slope, then b is the intercept. Now that is quite straightforward, but what we are interested in is nonlinear equations, things like quadratics, things like cubic functions, trigonometric functions, any function basically which is not a straight line. That's what we are interested in. So we want to find ways of actually solving such functions. So basically we are interested in finding the solution. The solution is also known as the root of a function. It's also known as a zero. So there are a bit of terminologies which people use. You can say the root to nonlinear equations, or zeros of nonlinear equations, or solutions of nonlinear equations. It's just one and the same thing. So basically, the function we are interested in, whatever function it is, this nonlinear function, we want to know the value of x at which the function has got a value of 0. So basically, we are looking for the value of x where f of x is equals to 0. When you know this value of x, which makes the function f of x to be equals to 0, then you have found the solution, or the root, or the 0 of the function. And that's what we want to do. Any function we want to be able to find, we want to have a way of going about things so that we can actually find the solution to the said function. Here is an example of a quadratic function. Now when it comes to a quadratic function, quadratic functions, you can work them out using pen and paper. So you can either use factorization, you find the factors, or you can use the quadratic formula, the famous quadratic formula. You'll still be able to do that. The point is, a quadratic function can be solved using pen and paper. So we say you can solve it analytically. Okay? However, there are many equations which you cannot solve using pen and paper. We say that they don't have analytic solutions. Okay? An example of a solution of a function which is difficult to solve using pen and paper is this one: f of x is equals to e to the power x plus x is equals to 0. So you have to find the value of x which makes this whole thing become equals to 0. It is quite a task, and luckily there's a way of solving these equations, these ones which cannot be solved analytically. There's a way of solving them which is known as numerically. Basically, you are using a computer, okay, those days. But in your case, yes, you're using a computer, but in your case, when you write your exam, you're not really allowed to go with the computer in there. But what you're going to be doing is you'll be mimicking what the computer does. The steps which the computer follows. Those are the steps which you're going to be following as you try to find solutions to these problems. So in your case, as you write your exam, as you write your tests, yes, you do it on pen and paper, but the stuff you're doing on pen and paper, basically those are the steps, or we call them algorithms, which a computer is going to follow. An algorithm is a set of instructions which a computer follows as it tries to carry out a specific task. In this case, the task is to find solutions to nonlinear equations. Okay, so one of the reasons why we do this is because, one, the function or the equation cannot be solved. The function or the equation cannot be solved using pen and paper. Or you can solve it using pen and paper, but it's very, very difficult to solve using pen and paper. When it comes to using a computer, computers are fast. Okay? They can do things very, very fast. Computers can repeat things. They don't get tired as long as there's electricity. Computers will obey, and they can carry out your instructions at lightning speeds, basically. Okay? So, apart from some equations not having analytic solutions or being very difficult to solve, you also sometimes want to solve things very, very fast. It might be a quadratic function. You can solve a quadratic function using pen and paper, but maybe you want to solve it very fast. Or maybe I've got a bunch of quadratics, maybe I've got 100 quadratics or 50 quadratics which you not solve. So as much as it's possible for you to solve the 50 quadratics or the 100 quadratics, it's going to take you maybe weeks or a week, but you want the solution right there and then. And that's where a computer comes in, because computers are very, very fast. Okay, so you can obtain your solutions quickly. So we make some assumptions about what kind of functions we're going to be looking at. There are different types of functions, but we have to kind of restrict ourselves in this course about what we're trying to do. So the kind of functions we're looking at are something called single valued functions. Functions which have got a single root. The answer, the root is single. You might have a function which has got multiple roots. If a function has got multiple roots, we can still find the solution to that particular function, but we have to restrict ourselves to a specific region so that we end up meeting this condition to say the function has got a single root. It's possible for a function to have more than one root. Okay? Like in the case of a quadratic, we know quadratics have got two roots, x1 and x2. But if you're going to be solving a quadratic using these methods we're trying to look at here, you need to restrict yourself to that region where there's only one root which you're interested in. Then the other bits assumption we're making is that these roots we are looking for are actually real. They are not complex numbers. Okay, so we're talking about real roots. So with these two assumptions of our functions being single valued and also our functions having real roots, we proceed to look at the methods we're going to use. So there are two methods we're going to use. There's something called bracketing methods and there's something called open methods. Now, the difference between a bracketing method and an open method is as the name suggests. In one case, you actually, along the x-axis of the xy plane, because your function f of x will have to cross the x-axis somewhere, okay? So near where it's crossing the x-axis, you create a closed bracket. So you have an interval of a lower bound value a, and an upper bound value b, like here. So you have got a and b, where a is the lower end of the interval and b is the upper end of the interval. So with a bracketing method, you need two guess values. You need an a and you need a b. Then for them to satisfy the bracketing thing, the solution to your function needs to be in between a and b. Okay? The solution to the function needs to be in between a and b. If you choose a bracket a comma b, then this bracket does not enclose the root, then you will never find the solution. So it's very, very important that you actually make sure that the bracket you have chosen actually has somewhere in between a and b, the function f of x crosses the x-axis somewhere in between a and b. Okay. If that is the case, with a bracketing method, then you are guaranteed to find the solution, because when you are doing a bracketing method, what you do is you slowly, step by step, you shrink the bracket. So the bracket, you make the bracket become smaller and smaller and smaller and smaller after every step. As the bracket becomes smaller and smaller, the intervals a and b are going to become closer to the root of your function. When we see that, because when you see that actually, okay, this is close enough, then you can stop. Okay, so that's about bracketing methods. You need to choose two values, in the lower end of the interval, in an upper end of the interval. Then, as you choose these two values, a and b, the next thing you need to do is you need to make sure that the function lies between the root of your function lies between a and b. Then after each step, you're going to shrink the bracket. We're going to see how to do that, okay, later on. Okay, so the only method we're going to look at here, due to restrictions in time and also because the method always works nicely, is something called the bisection method. Okay, so we have an interval, then we start bisecting it like that. Okay, so here you've got a closed interval. The other method called open methods, as the name suggests, open methods you your solution, you might know where, you might have a rough idea of where the solution is, okay? But you do not have a closed interval. You don't have a bracket. So basically, in this case, you only choose one guess value, okay? Then after every step, you update this value so that hopefully your guess value x naught, this one, that's your guess, that's how we denote the guess value. Your guess value x naught, hopefully after each step, so you update your value, you do something to this x naught, then you end up with x1, okay? You end up with x1. Now you are hoping that x1 is closer to the root, okay? If that is the case, then you get x1, you do the same thing you did to x0, then you end up with x2. Then you're hoping that x2 is closer to the root than x1 and x0. Then you keep on doing this updating of the guess value, okay? You keep on updating this guess value until you think you are close enough to the solution. Okay, so until you think you're close enough to the solution, we are going to look at two open methods. Something called Newton-Raphson method. It works quite well and it's neat and fast. And something called second method. The second method is an extension of the Newton method. So basically it's one and the same method, but it is an extension. It's a modified Newton method so that you can actually work out things. One of the things you need with the Raphson method, as you are going to see, is for a particular function you're trying to find the solution for, you need to be able to work out the derivative, okay? So if you've got f of x, you've got f of x, you need to be able to work out the derivative of that, the first derivative of that particular function. But you might have a function whose derivative is not easy to work out. And that's where second comes in. When you have a function whose derivative is difficult to work out, then you can use second. So between bracketing methods and open methods, the difference is, for a bracketing method, as long as you make sure that your brackets a comma b is surrounding the solution, your function crosses the x-axis in between a and b, then you can always find the solution. The backside to a bracketing method like bisection is that it is slow, okay? It is slow, like slow, but it is reliable. If your bracket has been chosen nicely, you can always find the solution, okay? On the other hand, with open methods are faster, okay? Open methods are faster, but they are not very reliable. Sometimes you can find the solution, sometimes the computer tells you, I've failed to find the solution, okay? So they don't always converge to the solution, but they are faster. When they converge, they are really quite fast and convenient, as we are going to see. So, unless people have got questions, we're going to start with bisection. So, with bisection method, and that's part of the reason why we are also using the notebook, so that we can actually see, we can have a picture of what it is we are actually looking at. I'll reduce the zoom a bit. Okay, so with bisection, we're going to use an example, which is in this case is this function here. Yeah, so suppose and we'll be using examples to solve some of these things so that you can actually also get yourself some practice thing. Okay, so suppose you have a function f of x which is equals to x to the power 5 minus 2x to the power 2 minus 3 equals to 0. which crosses the x-axis at some point. So basically, this is the function we have. We want to find the value of x where f of x is equals to 0. Since we are using Python, that's good and fine. So what we're going to do is, let me kind of a bit restart and clear the kernel. So what we're going to do is we're going to create a function. We're going to define a function f of x, and we're going to see what the function f of x is going to be exactly this. We're going to define a function f which accepts the value x. Then inside the function we are going to return x to the power 5 minus 2 x squared minus 3 for each particular point. Okay, so I run that bit. Okay, then here what I have here is I'm trying to, because I'll need a graph. Okay, I'll need a graph. So for me to have a graph, what I do is I have to import matplotlib. Then inside matplotlib I need to import pyplot. Okay, so I say import matplotlib. Now this is a long word, matplotlib.pyplot. It's quite long, so I import it as an alias as plt, which stands for plot. Then of course this other next line here, this is a magic command. It basically tells, I'm actually telling the Jupyter notebook, say, look, wherever I say plot, that's where you're supposed to kind of like put the graph there. Okay, then next here I also import numpy. Numpy is a module, and I import numpy as np. So basically I've got two aliases, one plt, which I'm using for, which I'm going to use for the plots, then the other one is np, which is the alias for numpy. If we are going to plot things, we need a list of numbers. Okay, that's where numpy comes in, because it allows us to quickly and easily generate a bunch of numbers, a list of numbers which we can use. So I run that. Okay, so it runs. Okay, no complaints. So the next thing I do is I want to generate a list of x values. Yeah, I want to generate a list of x values. So here I say x equals to numpy.arange. Now this one, numpy.arange. Arange is a function which is found inside numpy, and that's a function you use for generating a list of values. What kind of list of values do I want to generate? I want to generate a list of values which starts from 0 all the way up to but less than 2.1, and I want these lists in steps of 0.1. Very carefully, I want to generate a list of values starting from 0 up to but less than 2.1, and I want those values in steps of 0.1. So when I do that, I run that, that's what I get. Then I print x. What have I produced? That's what I have. So that's a list of numbers I've generated using numpy. So I have 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, all the way up to 2 in steps of 0.1. Okay. Then I ask Python what kind of object is x. Python tells me x is a numpy array. Okay. So now that I have my values of x, I want to put each of these x values in this function so that I can get the corresponding value of that function at each of those points. I want to get a value of x. Okay, but for me to do that, I need to define a function in Python. Then once I define that function in Python, I can give it the array. Then Python is going to quickly give me whatever each of those functions are at that particular point. And that's what I do here. I'm saying define the function f of x. So f of x, this is a mathematical thing here, but basically this is it's a one-dimensional function. Okay, so basically you have got f So the function f accepts a value of x. Now when you give this function a value of x, what's going to do is, there's someone who is, can we click on our microphones if you're not speaking? Click out your microphones. Click on your microphones. Perseverance and Mutukola, can you click on your microphones so that it becomes like Limpo's microphone? Perseverance, click on your microphone. Okay, so how do we do this? So basically what you have here is a function f. This function f accepts a value of x. Then when it gets this value x, it raises to the power 5, then minus 2x squared, then minus 3. Then it gives you a value of okay. So how do we define the function? So for you to define the function in Python, you need to start with DEF. DEF means define. Okay. So DEF, then after DEF, there's F there. F being the name of the function. In this case, the name of the function is just a single letter. Then after the name of the function, you have a bunch of 2 parentheses. Then inside the parentheses, the argument or the parameter which the function is supposed to accept. In our case, our function is only supposed to accept 1 parameter. Then inside the function, the body of the function, there is a return statement there. Then what are we returning? We are returning x to the power 5 minus 2 times x to the power 2 minus 3. So that way, when you put a value of x, you give this function f a value of x, it's going to get that value of x, it's going to raise to the power 5, then minus 2 times 2 to the power 2 minus 3. Okay, so we run that, Python accepts. Okay, now when you do the following, when you do this now, when you do this, that is what you get. So you get a bunch of values, an array, the value of the function at each value of x. You can, if you don't like the array bits, you can put the whole thing in a print like that. Then you get something much neater which looks like that. So basically these are the values of the function. Excuse me. Hello? Okay, so those are the values of the function at each particular value of x. Okay, and if you ask what this is, Python still tells you that is an array. So now we proceed to make a plot of the x values. So with the values of x, we say print x somewhere here, there. Those x values, print x, and these values of f of x. We proceed to make a plot. So how do you make a plot? So you start with PLT. So you're telling Python you want to make a plot and you want to use matplotlib. So PLT, then after PLT you say plot. Then inside plot you're telling Python, first of all, which one is the x value. You want to print the values of x against the values of f of x. Then after you make the plot, you want a label. You want to add a label. The label is that, which is the name of the function. Then on the y-axis, plt.y label, you want to show f of x. Then on the x-axis, you want to show x. So plt.x label x there. Then you want to show a legend. Then you want to show a grid. Then plt.show. So when you do this, this is what you get. Okay, so you can see on the x-axis. So here on the x-axis, you're with your values of x. You're with the values of x from 0 to, if I can kind of like, yeah. So from 0 to 2, then on the y-axis here, you're with the values of that from okay, there. Yeah. So here you're with the values of x from 0 to 2, and they're in steps of 0.1. Then you have got the values of y, and the label there is x, so that's how you add the x there. Then that's how you add your f of x there, and that's how you add this, your legend there, using these lines, these 1, 2, 3, 4, 5, 6 lines, and like that. So we have our graph. Now, if you follow this graph, you can clearly see at f of x equals to 0, it cuts the x-axis somewhere close to 1.5. So there is a point where the function has got negative values, then it crosses the x-axis, then it starts having positive values. The point where it's cutting the x-axis, that is our solution. That is our value of x, which we are looking for. Depending on what you want, if you want to use a bracketing methods and opening methods, you can find the solution. That's up to you. Okay? So, like I've said, we are going to start with a bracketing method, which is bisection. So, with bisection, you choose two values. Okay? You choose two values and you make sure that those values are actually enclosing where the solution is. You can choose the value of A, the lower bound of the boundary to be 1. You can choose B to be 2. The thing is, the larger your brackets, the more steps you have to do to find the solution. The smaller your brackets, the less the amount of steps you have to do to actually find the solution. Okay. So Jesus. What lives there, Adrian? Okay, Mukutura, are you the one who lives near the train? Can you click on your mic? Mukutura, can you click on your mic? So it's either he's listening or he's ignoring us. We don't know. Okay, so let's proceed. So the thing is, in bisection, when you will be doing the bisection, with the computer, if I have given you a graph like this, with the computer you can visually see, okay, you can see that, okay, this function cuts the x-axis there, so there must be a solution. Okay, however, things were not always this easy. Okay, it was not easy. It was not always easy to produce a graph like I've just done. Okay, so we had to develop a thing, okay, where if you chose a bracket, you would want to find out if this bracket, in this bracket I've chosen, there is a solution. So the first thing is, when you choose a bracket, you need to check if that bracket actually contains a solution. And how do you do that? It's by working out the value of the function at each of the points you've chosen, the bracket points. So you work out f of a then you work out f of b. After you work out f of a and you work out f of b, then you multiply f of a times f of b. Okay? So, in our case here, if you chose a to be 1, okay, if your value of a, you've chosen a to be 1, then f of a is going to be negative, as you can see here. Okay, f of a is negative. If you chose b to be, sorry, you chose 2 to be b, b is equal to 2, then you do f of b. F of b, as you can see, is going to be positive. So, with this choice, you've got f of a, which is negative, and f of b, which is positive. If you multiply f of a times f of b, f of a being negative and f of b being positive, you get a number which is negative. And the fact that the number is negative means that it's less than 0. So when you multiply f of a times f of b, then you get a number which is less than 0. It is telling you that in this bracket you have chosen, your function has crossed the x-axis, because f of a is negative, f of b is positive. So it's telling you your function has crossed the x-axis. If, on the other hand, you decide to choose a bracket from a to 1, say your a is 0, your b is 1, f of a is going to be negative, because as you can see the function is negative here. Then if your b is 1, then f of b is going to be negative. So when you come here, when you multiply here, f of a, which is negative, and f of b, which is negative, it's going to give you a number which is greater than 0. So you end up having f of a times f of b being greater than 0. When f of a times f of b is greater than 0, then it's telling you your function has not, in this interval you have chosen, your function has not crossed the y-axis. That is, if f of a and f of b, sorry, has not crossed the x-axis, that is, if f of a and f of b are negative. You can choose to say, let's say between, you can choose a value of, let's say somewhere 1.7 and 2 as your bracket, or 1.6. So your a is 1.6, your b is 2. If a is 1.6, then you can see f of a is positive, f of 1.6 is positive. Then if your b is 2, then f of b is positive. If you work out this f of a times f of b, it will come out to be a positive number. That is telling you that in this interval, your function has not, it's either it has already crossed, it has already crossed the it has already crossed the x-axis. So if f of a is positive, f of b is positive, then it's telling you either your function has already crossed the x-axis, or it has not yet crossed the x-axis. Okay? If it's negative, both of them are negative. So the only thing which matters is if you multiply these two guys, if they are greater than 0, if they are positive, then either your function has crossed the x-axis, not already crossed, or not yet crossed in that particular interval. So what we are looking for are values of a and b such that if you multiply this a and b, you end up with a product which is less than 0. When your product is less than 0, then we know that this function has got a solution between a and b. Okay. So, once this condition has been satisfied, this condition has been met, the next thing you're going to do is you're going to guess your solution. Okay? So, this bisection is basically a process of guessing what the solution is. And how do you guess a solution? You're going to add, your guess solution is C. You're going to add a plus b, then you divide by half. So basically your solution, your first guess is going to be half a plus b. So you add a plus b, then you divide by half. That is going to be a solution, C. Okay, which is just the midpoint of your interval. Once you have your C, the next thing now you do is you check the following condition: f of a multiplied by f of c. F of a multiplied by f of c. You want to check if between a and c, that's where the solution is, or if c is actually your solution. Okay. So the first condition you check is if f of a times f of c is equals to 0. If f of a times f of c is equals to 0, that would mean that c is where the function is crossing the x-axis. F of c is equals to 0. Okay? In that case, if this condition is met, then you are going to make a become equals to c, then you're going to make b become equals to c. So both a and b, they become equals to c, because that is your solution. The reason why you're doing this, a becomes c, b becomes c, is because for you to work out the solution, this is how you work out the solution. It is a plus b divided by half. So if this condition is met, then you have a solution. So you make a become equals to c and b become equals to c. However, this is very, very rare. This doesn't happen, and usually we don't bother ourselves. We never get to that position. We only do things up to a certain extent. So that's one condition. F of a multiplied by f of c is equals to 0. The next condition you check is f of a times f of c is greater than 0. F of a times f of c is greater than 0. What this means is that if, let's take for instance, you have an interval here, right? Let's say our interval is from let's say for instance our a is equals to 0, our b is equals to 2, right? If our a is equals to 0, our b is equals to 2, if we do this, so here we start with this one. If our a is equals to 0, our b is equals to 0, is equals to 2, this one, f of a times f of b, f of a is negative, f of b is positive. You multiply negative times positive, you get something less than 0. So we know that there's a solution between a and b. Okay? So if there's a solution between this interval, we guess what the solution is. C is equals to half a plus b. So a is 0, b is 2. So 0 plus 2 is 2. 2 divided by half is 1. So our guess solution is 1 here. So we are here. This is where c is at 1. Okay? So your a is 0 this side, your c is 1, your b is 2. Here, if I multiply this one, f of a times f of c, f of a is some negative number here, f of c is some negative number here. So I'm multiplying a negative times a negative. So I am not meeting this condition. F of a times f of c being equals to 0. This condition is not met. However, here, f of a is, my a is 0, so f of a is negative. My c is 1 here, so f of c is negative. So f of a times f of c, negative number times a negative number is a positive number. There. So in this case, what does the bisection algorithm say? You have to make a become c. So you set c to become a, and you set f of c to become equals to f of a. So c becomes a. So your a moves from being 0, a equals to 0, now a becomes a equals to c, because c is 1. So a becomes equals to c, which is equals to 1. So your lower bracket has shifted from being at a equals to 0, it's now at a equals to 1. So it has shrunk by half on one side. The lower end has shrunk by half. So now your a is equals to 1. Okay, your a is equals to 1. Your b is still equals to 2. Okay, your b is still equals to 2. Then here, there's another condition here. If f of a times f of c is less than 0, then you make b become equals to c, and f of c and f of b become equals to that. So we are here. Okay, we are there. That's why we have just done this. So we have made our a become equals to c, we have made our f of a become equals to f of c. So now our new value of a is 1, and our value of b is still 2. So we recalculate. You do a recalculation. Next, recalculate a new c and check for f of a times f of c. So how do we work c? The same way here. So c is equals to half a plus b. So you work out a plus b. So our a is 1, our b is 2. So 1 plus 2 is 3. 3 divided by half is 1.5. So our c is now 1.5. And 1.5 is where? 1.5 is just very close to where we are there. Very, very close to where we are. 1.5. Okay. So now you do the following. You check this. You check this condition. F of a times f of c. If it's equals to 0, then you make a equals to 0, then you make b equals to that. Then, or you check this. F of a times f of c, that. Now in this case here, from what I can see, this 1.5 is just in front of where the root is. Okay, so f of 1.5 is slightly a positive number. Okay, so what we actually have is our a is 1, so f of 1 is negative, then our f of c is positive. So we are multiplying a negative number f of a times a positive number f of c. So negative times positive is not this one. It is not this one, but it is this one. We get ourselves a number, a product which is less than 0. So f of a times f of c, we get a product which is less than 0. If our f of a times f of c is less than 0, then we make b become equals to c, and we make f of c become equals to f of b become equals to f of c. So in this case, when we make b become equals to c, basically what we are doing is this upper boundary here, the 2, we are bringing the 2 to 1.5. Okay, so we shrink the upper boundary from being equals to 2, we bring it to 1.5. So now we have a boundary which is between a, which is 1.1, a is 1, and b is 1.5. Okay, so now that you have got a new value of a, which is 1, and you have got a new value of b, which is 1.5, we go again and we work out c. How do we work out c? So c is going to be equals to half 1 plus 1.5. 1 plus 1.5, that is 2.5. Then 2.5 divided by half, that gives us something like 1.25. So our new value of c is going to be 1.25, which is this one here. So our c is going to be there. The c value is always in the midpoint between a and b. So our c value is going to be there. Okay, so that's where c is. So we have got a is at 1, then we have got b, you have got a is at 1, you've got c is 1.25, then you've got b, which is at 1.5. Then you come back and you check these conditions. F of a times f of c. F of a is there. A is 1. And so f of a is negative. Okay? then C is 1.25. F of C is negative also. So you've got f of A is negative, f of C is also negative. So a negative quantity multiplied by negative quantity, you end up having a positive, which is this condition here. So f of A times f of C is a positive. Okay? So if it is positive, then you make C become equals to A. And you make f of C become equals to f of A. So what does that mean? So our A, which is at 1, is shifted to C, which is at 1.25. So the new value of A becomes 1.25. So you have got an A at 1.25, you've got a B at 1.5. Then again, you repeat the same process. You work out C. Okay? So in this case, your C is equals to half, then your A is 1.25 plus your B, which is equals to 1.5. So 1.25 plus 1.5 is some number. Then you divide that number by half. So you end up with some quantity which is between 1.25 and 1.5, somewhere in the middle there. That's where your C is going to be. Okay? Then your A value is 1.25. Your C is somewhere between let's say 1.3 something, maybe 1.35, somewhere there. Then your B is still 1.5. So you work out this again. You follow this condition. You multiply f of A times f of C. Again, this condition remains because f of A is 1.25. That's negative. Then your C is going to be somewhere in the middle there. That is another negative. So you multiply a negative times a negative. So what does that tell you you're supposed to do? You make A become equals to C. So you can clearly see that A is shifting. It's shifting towards where the solution is. So A keeps on shifting until A and B are very, very close to each other. So when do you stop? When you stop, it depends on you, because every other time, remember, after you have to work out a value of C. So you can put a condition where to say, I want to stop when between two successive values of C. We started with the first value of C, the second value of C, the third value of C, the fourth value of C. So you keep on finding different values of C. You keep on updating C because C is your root. Okay? So you set the condition which says between one value of C and the other one, I want to stop when the difference between this value of C and the next value of C is less than a certain number. Then when that condition is met, then you stop. So when you stop, you have got a value of A and the value of you've got a value of A and the value of B by the time you're stopping. Then you use those two values of A and B, you work out a final value of C using that value of A and B. So the value of A and B you found, the final ones, your final A and your final B, you use them, you add them, then you divide them by 2. Then you would have got yourself a value of C, which is very, very good approximation of what the solution is. Okay, so basically this is how the whole thing is supposed to be done. So you basically have to work out what you call successive values of C, and you can actually put some criteria there like that. So if this is the odd value of C minus the new value of C, you can say between the odd value of C and the minus the new value of C, the difference should be this much. If the difference is less than this much, then you tell the computer to stop. Or you can have the odd value of C minus the new value of C divided by the new value of C. This is what's known as a relative difference error between the values of C. Then you multiply it by 100%. So you're saying maybe you want a precision of 10, when you say 1%, 1% is actually basically a difference of 0.01. Okay, so if the difference between the one value of C and the other value of C is 0.01, then you tell the computer to stop. Maybe you want a precision of 0.00, something like that. Then basically that's what this means. So you are setting the criteria for when the computer should stop. Otherwise, it's going to continue doing this unnecessarily, even when it has found an answer which is actually practical. So you can set a percentage. Say, I want the error between the difference between two successive roots to be less than 1%. So you're looking for a solution which is less than 1%, then you can do that. Okay. Apart from that, you can ahead of time. You see, when you are doing bisection, you are reducing, each step you do is reducing the bracket, right? Which means that there is always a maximum number of steps you can carry out, because the bracket keeps on shrinking. Okay, so you can't carry on doing the shrinking forever. Eventually it has to stop. So basically, bisection ahead of time, there's a way of knowing how many, you can know ahead of time how many steps you should carry out. Okay, and how do we do that? How do we know ahead of time how many steps we should carry out? Well, by using this formula. That formula there. By using that formula. What that formula is telling you is basically is that the number of times you're going to do the bisection is equals to the logarithm, but the logarithm of, first of all here, that one there is the delta x naught. That is the bracket you start with. The initial bracket you start with, the size of the initial bracket you start with. Okay? Delta x naught, which is the size of the initial bracket you start with, then divided by here, this one at the bottom here, is the error you have set. Do you want to do it up to 1% or up to 10%? So your initial bracket you have set with divided by the error you have set. Okay, and that, like that, ahead of time, you can actually kind of find out what the solution is supposed to be. During an exam, normally would tell you to say, repeat the bisection process maybe about 5 times, because you can't do it indefinitely, otherwise you'll not finish your exam. So we tell you, do the bisection step typically about 5 times. So you work out 5 values of C, then your final value is whatever it is. So basically that's what it is. Any questions? So basically that's bisection. So basically that's bisection. Any questions? Do we have questions? Okay. So, if we don't have any questions,
okay, I can get you now.
Sorry?
I was saying you can continue, I can get you.
Okay, so if you don't have any questions, that's fine. Remember, I record these online classes, okay? I record them. So I have a recording of these. So, I also told you guys, say I've set up a Google Classroom. So I hope you, did I send the invitations to you guys? Did you receive invitations for the Google Classroom? Okay, so I'll
did.
Sorry? Okay, so I will check. So the recording,
We received.
yes. So basically, what we are going to be using the Google Classroom for, we're going to be doing this two different ways. Okay, one, on the Google Classroom, I will upload the notes, the PDF. Okay, the PDF of what we have just been discussing. So I will upload the PDF there on the Google Classroom. Then, when the PDF is done, I upload it there. Then also the recording, because I record my screen. So the recording of what I'm explaining, I also upload it there. So the videos, I'm going to initially keep them on my Google Drive. So using my Google Drive, I'm going to copy a link which I'm going to post in the Google Classroom. That way, you can go back and watch my explanation and what I'm saying and what I'm doing. Okay? So that studying is easier. So that you don't have to come and ask me. You can just go and watch the video and see how something was done. So that being the case, the other thing I'm going to do is I will try, we're going to do two ways. Okay? One, we're going to solve the problem following the same steps which the computer is going to follow. We're going to solve the problem with pen and paper. In the other case, we will solve the problem using Python. Okay, so we're going to do it with pen and paper. So this is how it will be done with pen and paper. You do it for so many steps, not a lot of steps. Then the other case, we're going to solve it using a computer. Then we compare our solutions to say, okay, are the solutions we're getting by hand and the solutions we're getting by computer the same or not? Or are they close to each other? Of course, if they are close, that's good. However, as you do things by hand, I can assure you the computer is going to do something in less than a second. So whatever you're doing by hand, the computer can do it in less than a second. So computers are infinitely faster than we are. Okay, so we need to take advantage of that. And basically that's going to be the thing we're going to do tomorrow. So we are going to go through the same bisection steps tomorrow to solve that problem where we have got the cave I was showing you. So we are going to solve it by hand first. How do you solve it by hand? What is the answer? Then after we solve it by hand, then we are going to make our own bisection problem, our own bisection computer program, which we're going to use to solve the same thing. However, Python also, Anaconda also comes out of the box. It comes with a solver called bisect, a bisection method, which means you don't really have to actually make your own bisection method. There's a bisection method which has been made by professionals. Okay? It works very, very nice. And it's just one line. Then the answer comes out. So we are also going to go through the same process, but we're going to create our own crude bisection. So with our own crude bisection, it is going to work. It will give us some answer, but the whole idea of what I'm trying to do is we want to avoid, yes, we're going to learn how to do the program, how to make the program, the bisection program, but if something has already been made, the idea is you should learn how to use the stuff which is coming from the shop. Okay, not go into your kitchen and you start creating your own stuff. If you go to the shops and something is not there, then you can come back and start making your own juice, whatever juice you want to make, whether it's from, I don't know, from whatever fruit you want to make. If it's already at the shops, that's fine. Okay, but there is no harm also in creating your own stuff. The only thing is, whatever you create is not going to be as efficient. It might not be as efficient as the thing which comes out of the box. Okay, so that's that. So we're going to be doing 1 hour things. Okay, we're going to be doing 1 hour things. And the other thing is the target is each week, by the end of each week. So if you're doing 1 hour, Monday, Tuesday, Wednesday, Thursday, Friday. That is 5 sessions. Hopefully, at the end of each week, we finish a topic. Okay? If we manage to do that, it means at the end of 6 weeks, this course will be over. So basically, that is next month, in the second week of October, the course will be finished. Is that clear? So if we keep up with the pace of 1 hour, 1 hour, 1 hour with 5 sessions, then it should be possible that by the end of next month, by next month, in the second week, then this course will be over. We would have done it in 6 weeks. But we would have done it in 6 weeks because we are doing more hours than Nankan. Than we are supposed to do. We are doing more hours. Okay. What I want to do is I want us to finish. We reach the end phase. Once we reach the end, as we are reaching the end, I'll also be giving out tutorial questions so that you can try to practice. When we reach the end, then we can do tutorial questions. Okay. After we finish doing tutorial questions, then you can write your test and your test 1 and test 2. Or the other option is we do topic number 1, which is this one this week, then topic number 2 next week, then number 3. Then after 3 weeks or after 4 weeks, we do a test. Okay? After 4 weeks, we do a test. So it means, I think that's better. As we are doing, when you finish a topic, we do a tutorial sheet. Okay? When you finish a question, we do a tutorial sheet. Most likely, I don't know which one is going to be easier because these things are tedious. So I might solve the tutorial sheet ahead of time, showing you how something is done. This is how you do it, this is how you do it, like that. If it makes sense, then we discuss the solution. If it makes sense, normally I think that's how this course is done. The lecturer gives the solution. Then you discuss the solution. You explain, this step, you do this step, then you do this, then you do this and this. If there's somewhere you don't understand, then you ask. Then we discuss what you don't understand. Then we move on. Okay? So, what I'm going to do is, I think we will work out a few questions. Then the remainder of the questions, maybe I'll work out 2 to 3 questions. I'll work out 2 to 3 questions to demonstrate how a step works. Then the rest of the questions, you have to work them out. Okay, so I think that way we can write our tests 1 this month. Then at the end of whatever it is we're having, that you can also write your test 2, then exams. That will leave us with labs. Labs will still have to be done. We've got a bunch of labs which need to be done, and those will still have to be done. We can continue meeting. Labs, I've set, if you look at the timetable, I've set the labs for the weekend from 11 hours to 13 hours. Is it 11 to what? Is it 11 to 14 or whatever, 10 to, but I think it's 11 to 14 for 3 hours. There are many labs which need to be done, and the labs have to be done because the labs account for 15% of your marks. Okay? So we can discuss, how do you do this? How do you do that? People can be sharing the screens, their screens on the computers. If you've got a Google Meet and a meeting, you can share a screen. Oh, I'm doing this, like that. You show us how you're doing something. Okay? Using the knowledge which we have of the Python thing. The other thing I want to announce is UNZA and the Mishek, they continued learning the Python because they came behind. So while you guys went home, these guys continued learning the Python class, the one on Sunday. So my advice is, we have the lab, we do the labs Saturday, 11 to 14. Sunday you go to church, if you go to church, in the morning, 15 to 17, those students who can afford to come, they can come here, in this computational lab, like he is here, okay? You attend the class live. If you can't afford to come, you're very far, your home is very far, then you will join us using Google Meet. We are going to share the screen as we are discussing things, okay? So that you can also join in the discussion and you follow things. Because there are topics like how to use NumPy and Matplotlib, the things we need for this computational stuff for it to work properly. Those things need to be learned. And even after you're done with the course, the course is not just for you to pass the exam, like the way business has always been done. Then you pass the exam. After you pass the exam, then you forget. No. Once you learn Python, the way I'm trying to teach it, once you learn Python, then even after you finish the exam, you should continue using Python to solve things so that your experience in Python increases. As you are aware, there's a problem in this country with youth unemployment, okay? So if you're going to look for a job, or if you can't look for a job, you have to create your own job. Knowing how to program a computer is a very, very big advantage. Okay, you might not create your own job, but if you're going to look for a job, then you're telling your people, the people are trying to give you a job, say, oh, okay, I also know how to program computers. They ask you, okay, with what? Show us what you can do. Right there and then, if you can show something, that's a very good, big plus. Okay, so it increases your prospects of employment. Then also, if maybe you want to run a business, there's some kind of business, computer-based business you want to do, it's helpful that you're able to tell your computer exactly what it is you want the computer to do for you. The problem we have is effectively communicating with the computer, telling the computer what it is supposed to do. After you buy a computer, you spend so much money on this computer. The problem is people still don't know, they don't know how to tell the computer to work for them. Okay. So we are not in the business of just passing the exam. No. We are in the business of learning properly so that this thing, after you're done with this course, the way you use your computer should never be the same. And the computer should work for you. Okay? So basically that's all I have to say. So we are going to meet tomorrow. We're going to solve a problem. The same problem which you have, using bisection. Okay, unless there are any other questions, we'll stop here. So I will, stop the recording. Then, Okay, if you want to ask something, you can ask, but I'm going to stop the recording now. Yeah.